Hey everyone. So in this video, I'd like to talk about two different kinds of trigonometric identities, the power reduction identities and the half angle identities. So at this point, we've talked about quite a few different kinds of trigonometric identities, and I'd just like to reiterate that the value in having all these trigonometric identities is that they allow you to convert one kind of trigonometric expression into another. And so depending on the problem you're dealing with, you might be able to use an identity to make your expression to a more easy to work with one. And so one kind of conversion that's pretty frequently useful is taking powers of sine and cosine and rewriting your expression into one that doesn't involve powers of sine and cosine. In other words, reduce the powers in your expression. And so here I'd like to bring up this identity of power reduction of sine and cosine. And so these come from the double angle identities. I'm not going to rederive the double angle identities here, but you can, maybe I'll just quickly remind you that we can derive these double angle identities for sine and cosine, these first two, by looking at our angle sum identities with the angle sum x plus x. And so doing that gives you these two identities here, and you can derive the following two identities below by using your Pythagorean identities, taking this cosine squared of x and replacing it with 1 minus sine squared of x, or taking this sine squared of x and replacing it with 1 minus cosine squared of x. So the power reduction identities that I want to go over come from these two identities here. And so let me show you what I mean. So here, let me rewrite these. I'll write this in a slightly different order. Let's start with 2 cosine squared of x minus 1, right? That identity, or that expression is equal to cosine of 2x based on our identity above. And so here I can take this expression and I can isolate that cosine squared. I can add 1 to both sides of this expression, this equation, and we get 2 times cosine squared of x is equal to 1 plus cosine of 2x. And then dividing both sides by 2, this gives us cosine squared of x is equal to 1 plus cosine of 2x divided by 2. So let me rewrite that. So this is an example of one of the power reduction identities. Right, what does this expression allow us to do? Well, it takes our cosine squared of x, it takes a cosine squared, and it converts it into an expression involving no powers of cosine or sine. It just converts it into 1 plus cosine of 2x divided by 2. And so we can do something very similar for the sine squared function. We can take that bottom identity there, our bottom double angle identity there, that 1 minus 2 times sine squared of x is equal to cosine of 2x. And we can isolate that sine squared of x to give us an identity that lets us convert sine squared of x into a single power of cosine. So here, if I subtract 1 from both sides of this equation, we get negative 2 sine squared of x is equal to negative 1 plus cosine of 2x. Now dividing both sides by that negative 2 to get that sine squared alone, this gives us sine squared of x is equal to, and I'm not such a big fan of this negative in the denominator, and so let me factor out a negative from the numerator as well, right? So I can factor out this negative sign from the numerator, and that would, pulling out a negative sign from that first term gives us just a positive 1, and then pulling out a negative sign from that second term gives us a minus cosine of 2x. And so now that's divided by negative 2. And so we can reduce those two factors of negative 1 from the numerator and denominator, and we really get that sine squared of x is equal to 1 minus cosine of 2x, all divided by 2. So this is another power reduction identity. It lets us convert a sine squared into a single power of cosine. So let's take our power reduction identities and apply them to this expression, sine to the fourth of x. So we want to rewrite this expression as one without any powers. And so our power reduction identities, they really, they apply to these squares of sine and cosine. And so if I want to apply our power reduction identities, I need to rewrite our expression in terms of sine squared of x or cosine squared of x. And so this sine to the fourth of x, well, that's really the same as sine squared of x squared, right? This sine squared of x, that's just saying sine of x times sine of x. And if we multiply that with sine of x times sine of x again, or in other words, we square it, we get our sine to the fourth of x. And so we can use our power reduction identity here to rewrite this sine squared of x as 1 minus cosine of 2x divided by 2. And so this is the thing that's being squared inside. And so we don't have any way of getting rid of this square, so really what we ought to do here is we ought to apply this square and see if we can use our power reduction identities again. Right, so applying this square means that we would have to take our base and multiply it to itself, right? So 1 minus cosine of 2x all over 2 multiplied with 1 minus cosine of 2x all over 2. And so if we multiply these out, we multiply the numerator to numerator, denominator to denominator. And so here, let's do the numerators first. Let's take that 1 times that 1. We take the 1 times that negative cosine of 2x, so minus cosine of 2x. We take that cosine of 2x, that minus cosine of 2x, and multiply it to that 1. Giving us another minus cosine of 2x. And we take that cosine of 2x and we multiply it with that last term, that minus cosine of 2x, to give us plus cosine squared of 2x. So that's the numerator, but here we also have this denominator of 2 times 2, in other words, 4. And so here, we're almost there. The only problem is that now we have this even power of cosine, right? So we want to use the power reduction identity again. But maybe before we do that, let's sort of clean this expression up a little bit. So here, maybe I can sort of split this up as 1/4. Right here, this 4 in the denominator is saying divide all of the terms in the numerator by that 4. And so here we have minus cosine of 2x minus cosine of 2x. This is negative 2 cosine of 2x. And so I can write this as minus 2 cosine of 2x divided by 4. And then lastly, we have this cosine squared of 2x divided by 4. And right, so here, let's apply our power reduction identity. Right, so here our power reduction identity says, okay, if we have cosine squared of some angle, we can write that as 1 plus cosine of twice that angle all over 2. And so here, this expression can be rewritten as, well, we still have that 1/4. The second term, we can do some reducing here and rewrite this as cosine of 2x over 2. And this last term, well, that cosine squared of 2x, right, that can be rewritten as 1 plus cosine of double the input angle, so 4x all over 2. And then, well, that was the numerator. This is then divided by 4. Okay, and so we're almost there. Maybe let's really make sense of this last term here. This is like saying we have 1 plus cosine of 4x divided by 2, and we're dividing it by 4. And to divide by 4 there, that can be rewritten as multiplying by the reciprocal. So multiplying by 1 over 4. So this really comes out to 1 plus cosine of 4x over 2 times, oh no, sorry. We would just multiply the numerators, multiply the denominators, and we get 8 in the denominator here. And so there we have it. We have our final expression is 1/4 minus cosine of 2x over 2 plus 1 plus cosine of 4x all over 8. So now let's go ahead and talk about the half-angle identities. So the double-angle identities, they helped us compute, if we knew sine of some angle and cosine of some angle, they allowed us to compute sine of twice that angle and cosine of twice that angle. And so we were able to compute these with the double-angle identities. And so that half-angle identities, they allow us to reverse this. They say that, okay, if I know sine of some angle and cosine of some angle, well then I can use those to help me compute sine of half that angle and cosine of half that angle. And so let's derive these half-angle identities. And so they come from just taking the power reduction identities and taking them a step further. Right, so the power reduction identity for cosine said cosine squared of theta. This is the same as 1 plus cosine of 2 theta, all divided by 2. And so here, if I take the square root of both sides, right, if I have cosine of theta is equal to plus or minus the square root of 1 plus cosine of 2 theta, all over 2. So this is an example of one of the half-angle identities. It says that, hey, if I know cosine of some angle, in this case it's 2 theta, well, I can figure out cosine of half that angle, just theta. And so, sometimes this is rewritten as, this is really the same identity, but it's rewritten to really emphasize that half-angleness. So this might be rewritten as cosine of theta over 2 is equal to plus or minus the square root of 1 plus cosine of theta all over 2. This is the same idea. This is just saying, hey, if I know cosine of some angle, then I can figure out cosine of half that angle. It's really the same identity, just sort of expressed with a slightly different perspective. And so, we can write this for our sine function as well. If I have sine squared of theta, this is equal to, from our power reduction identity, 1 minus cosine of 2 theta, all over 2. If I take plus or minus the square root of both sides, I get sine of theta is equal to plus or minus the square root of 1 minus cosine of 2 theta, all divided by 2. And again here, if I know cosine of some angle, I can figure out sine of half that angle is really what that's saying here. And really, the same identity, just kind of rewritten in a slightly different way, just to change the perspective a little bit and emphasize that half-angleness. Really, I can rewrite this as sine of theta over 2 is equal to plus or minus the square root of 1 minus cosine of theta all over 2. And just to reiterate, if I know cosine of some angle, I can figure out sine of half that angle. So let's go ahead and apply our half-angle identities to this problem here, where we want to evaluate cosine of pi over 8. Right, so why can we apply our half-angle identities here? Well, we're trying to find cosine of some angle that we're not very familiar with, but it's half of an angle that we are familiar with. Right? This is half of pi over 4. And so how do we use the half-angle formula? Well, this is saying that cosine of pi over 8, this is equal to plus or minus the square root of 1 plus cosine of, well, twice that angle, pi over 4, all over 2. So the half-angle identity says, okay, we don't know cosine of this angle, but if it's half of an angle we're very familiar with, right? In other words, twice that angle is an angle we're familiar with, pi over 4, then we can use this half-angle identity. And so pi over 4, right, where is that on the unit circle? Well, if I just draw my unit circle here, pi over 4 is that 45-degree angle. And cosine of pi over 4, that's the x-coordinate on that triangle there, or on that unit circle. And that's the square root of 2 over 2. So here, this is equal to plus or minus the square root of 1 plus the square root of 2 over 2. And this is all divided by 2. And so I'm not a big fan of that fraction within a fraction. So maybe let's clear some denominators here. And we can do that by multiplying this fraction by 2 over 2. And so that entire numerator is multiplied by 2, giving us 2 plus the square root of 2. If I take the square root of 2 and I divide it by 2, then it gets multiplied by 2. Well, those undo each other and just leave me with the square root of 2. And then the denominator, that's, well, 2 times 2 is 4. And then recall that we can break apart square roots along division. So if I have the square root of a over b, this is equal to the square root of a over the square root of b. And so I can rewrite this now as plus or minus the square root of 2 plus the square root of 2 all over, well, the square root of the denominator, the square root of 4, that's just 2. So we've got a lot of 2's here, but that's okay. Now the last thing is we're evaluating cosine of pi over 8. That's the x-coordinate along the unit circle at an angle of pi over 8. And that's not going to have two different values. It's not going to be plus the square root of 2 plus the square root of 2 over 2, or it's not and minus the square root of 2 plus the square root of 2 all over 2. It's only going to be one of these. And this depends on what quadrant we're in, right? So pi over 8, here, this is some angle, some small angle between 0 and 90 degrees, right? It's this angle here, it's half of pi over 4. And so this angle here, that's pi over 8. Just a rough sketch of it. And looking at this point here, well, its x-coordinate is positive, right? It's on the right side of this unit circle. And so we know that here we should take plus the square root of 2 plus square root of 2 all over 2. Right, so here, this choice of sign depends on the quadrant of pi over 4, or pi over 8. Right, so the fact that this is in quadrant 1 means that the result of this cosine expression is going to be positive. All right, so let's do this again, but for the sine function. Let's evaluate sine of 165 degrees. And so 165 degrees, this is not one of our familiar angles, right? If I draw my unit circle here. Whereas 165 degrees, well, it's 165 degrees is 15 degrees shy of 180, right? So here, maybe the picture looks something like this, where this angle in here, that's 15 degrees short of 180 degrees. And so this is our angle, 165 degrees. And so sine of 165 degrees, that's really this y-coordinate on the unit circle, corresponding to this angle of 165 degrees. And so here we want to find sine of 165 degrees. Notice that this is half of an angle we're familiar with, right? This is half of 330 degrees. And 330 degrees, well, that's 30 degrees shy of the full 360-degree rotation, right? So here this is 30 degrees shy of the full 360-degree rotation. In other words, we can kind of see here that there's a 30, 60, 90 triangle that fits in here. Right? This is one of our very familiar angles where this is a y-coordinate of -1/2, an x-coordinate of the square root of 3 over 2. And so if I want to use our half-angle identity here, I can rewrite this as plus or minus the square root of 1 minus cosine of twice that angle, cosine of 330 degrees, all over 2. Right, the idea is that I can compute sine of 165 degrees by knowing that it's half of a more familiar angle, half of 330 degrees. And so this is plus or minus the square root of 1 minus, well, cosine of 330 degrees. Well, that's the x-coordinate of this point associated with the angle of 330 degrees. That's the square root of 3 over 2. And we can do the same thing we did in the previous example of clearing out the denominators to make this not a fraction within a fraction. We can clear the denominator and the numerator here to get plus or minus the square root of 2, take away the square root of 3, all over 4. And much like the previous example, we can break apart the square root across the division that's occurring, and we can rewrite this as the square root of 2 minus the square root of 3 over 2. And so we drew out this picture we drew out this picture of 165 degrees, right? That angle is in the second quadrant. That really means that the y-coordinate of that angle, or associated to that angle, is positive, right? So here, because sine is giving us the y-coordinate of that angle on the unit circle, our result here is going to be positive, right? So sine is positive in quadrant 2. Right? 165 degrees is an angle in quadrant 2. Sine gives us some positive angle, or positive y value, when we're in quadrant 2. So let's do one last example. Let's determine sine of x over 2 if we know that cosecant of x is equal to -7 and x falls between 180 degrees and 270 degrees. So let's unpack this a little bit. So we're starting with this idea that cosecant of x is equal to -7. Well, cosecant of x is the reciprocal of sine. So this is telling us that sine of x is equal to -1 over 7, right, the reciprocal. Now what does this last idea say here? 180 degrees, that x is between 180 degrees and 270 degrees. This is really saying that x is in quadrant 3. And so if we draw a picture here to make sense of x and sine of x, what we're really given here is that, well, sine of x tells us the y-coordinate on the unit circle corresponding to that angle of x. We're saying that y-coordinate is -1 over 7. So here's a y-coordinate of -1 over 7, just a rough sketch. And we're saying that our angle x is in quadrant 3. So here, this is our angle x. And we're saying that the point on this unit circle corresponding to an angle of x, well, we know that's -1 over 7, but we don't know the x-coordinate, or the first coordinate of that point. And so how could we find it? Well, we know that here, the sum of the squares of these two coordinates should equal 1. Right, so here, this is exactly, this second coordinate, that was sine of x. This first coordinate, that's cosine of x when we're talking about the unit circle. And so we're trying to figure out cosine of x here to really flesh out this picture. And so this will help us in a moment, but let's really take this and go with it a little bit. So we're saying that cosine of x, when we square it, and we add that with sine squared of x, right? So in that case, that's -1 over 7. We know we're going to get 1. And this is the Pythagorean identity. So cosine squared of x plus, right, sine of x is -1 over 7. So sine squared of x, that's 1 over 49. So subtracting 1 over 49 from both sides, we get cosine squared of x is equal to 1 minus 1 over 49. And so I can take plus or minus the square root of both sides to get cosine of x by itself. So 1 minus 1 over 49. Well, 1 is the same as 49 over 49. And this is the same as 49 over 49, take away 1 over 49. In other words, we've got 48 over 49 here when we subtract their numerators. And so here we can break apart square roots along the division symbol, right? So here this comes out to be the square root of 48 over the square root of 49. We can also break apart square roots along multiplication. So this is plus or minus square root of 16 times 3 over 7. And we can write this as plus or minus the square root of 16 over, or times the square root of 3 all over 7. So that's 4 square root 3 over 7. Or we can break apart this square root along the multiplication. So we have square root of 16 times square root of 3. And square root of 16 is just 4. So this is cosine of x. And cosine of x, right, it's not going to give us two different values. Cosine of x is this coordinate here. But we can see that this coordinate, or this point here, lies on the left side of this unit circle. It's going to be negative. Right, so here we know that cosine of x is negative 4 square root 3 over 7. So I'll rewrite that here. This is negative 4 square root 3, maybe I'll write it bigger. Negative 4 square root 3 over 7. Okay, so here, let's go ahead and apply this to what we're really trying to find. We're trying to find sine of x over 2. And the idea here is that we can use the half angle formula, right? Sine of x over 2. It's half of the angle x, right? X over 2 is half of the angle x, and so we can use our half angle identity here to evaluate this expression. It's plus or minus 1 minus cosine of 2 times that angle. So cosine of, maybe I'll write this as 2 times x over 2, all over 2. Right, the idea here is that we're trying to figure out sine of, some angle here, and we know that this angle is half of the angle x. And so we can use our half angle identity. So this is plus or minus the square root of 1 minus cosine of just x over 2. But we know cosine of x. Right, we know cosine of x is negative 4 square root 3 all over 7. So this is equal to plus or minus the square root of 1 minus, it's negative 4 square root 3 over 7, and that's divided by 2. And so if I'm going to subtract away a negative sign, well, I'm going to get this addition here. And so this is plus or minus the square root of, one thing we can do here is we can multiply by 7 over 7 here to clear out that denominator in the numerator, right? Make this not a complex fraction. This is 7 plus 4 square root 3 over 14. This is sine of x over 2. And again, the idea here is that here x over 2 is half of this angle x. And so I can compute sine of x over 2 by knowing cosine of just x. And cosine of x, that's negative 4 square root 3 over 7. And so plugging that in brings us to plus or minus the square root of 7 plus 4 square root 3 all over 14. And then the last thing we need to do is figure out whether we're looking at a positive value or a negative value. So because x is in quadrant 3, it's between 180 degrees and 270. Well, that's telling us that x over 2 is going to be between 135 degrees and 90 degrees. In other words, this angle x over 2 that we're really trying to evaluate sine for, right, it's in this region here. It's in this interval here. I don't know exactly what the value of that angle is, but it's in this interval here. And so sine gives us the y-coordinate, and the y-coordinates of any point along the unit circle in this region here, well, it's going to be positive, right? It's above the horizontal axis, it's positive. And so that's sine of x over 2 is positive square root of 7 plus 4 square root 3 all over 14.